Okay, this is a talk on muon system studies. I want to spend a little bit of time talking about sources of muons, something on the specification of a muon system. There are two candidate technologies, RPC detectors and scintillator detectors, that I'll discuss a little, and then I'll talk about some of the R&D issues. There are various sources of muons. Conventional electroweak physics, which I'll explain in a moment. New physics, the stuff that we're building this machine for. And then things like beamline muons. This unfortunately does not include a discussion of junk coming from the IR. We'll get into that a little bit later, perhaps. So if you look at this plot, which is known to everybody, you can find it in various places. You see that we're talking about femtobarn cross-sections. And in particular, I'm asking the question, which of these contribute to muons in the detector? And so I'm just going to talk a little bit about these higher cross-section cases. So what we do is we look at those curves at 500 JeV and 1,000. And the cross-sections are given here, just reading off the curves. And then we multiply by the branching ratio, in this case, of the W to mu nu, and that gives us the cross-section times branching ratio. Same for the Z. In the case of the Z, it's 3.3%. Then QQ bar, we look at the case where we have a B or a C going to a mu. In W pair production, one W goes to QQ bar, the other goes to mu nu. And in the case of TT bar, we look at any of these things giving a muon. And then there's the mu mu itself, for which we don't have to put in a branching ratio. So those things, when you do all that, you come up with about 2 picobarns, either at 1,000 GeV or 500. So that's a significant number of events. That's something like, if we have 100 inverse femtobarns a year, and we have 2,000, then we have 200,000. Then you have to multiply by some detection efficiency. But it's a substantial number of events. Now, what about the things that we're really interested in? And these have all been discussed here today, I think. So this is, in fact, the Higgs, where we're looking at 3 different graphs that produce Higgs. And now we'll ask how many of those things involve muons. This Higgs-Strallen cross-section certainly does. So that's our first candidate. And so those things are listed here much in the same fashion as we looked at before. Only now, you see, we're talking about really small cross-sections from my perspective. A couple of, if you sum down here, you start out with 130 femtobarns. You end up, in the case of where the Z decays to mu's, 2 femtobarns, where you look then at the other branching ratios of the Higgs itself to muons, you end up with 23 femtobarns. If you go to a Higgs at a mass of 350 for 500 GeV collisions, you end up with much smaller numbers. If you're at 800 JeV, then 33 is the sum of this column, a very small number of decays where you have the Z to mu mu, or in this case, about 10 femtobarns. This isn't totally rigorous. I apologize for the non-rigor. It only includes the branching ratios of Higgs to WW and V's to mu and so on. It doesn't include absolutely everything. But it's meant to focus and rivet our attention. Now, what about extraneous muons? And this is now a short discussion on what happens, where do we get muons from the beamline. And this graph shows the distance from the IP. So these are muons that are produced elsewhere, way upstream from the IP. You can get rid of them by collimation and magnetized toroids, and Tausche has two articles, one in the CGIS proceedings and one in the Fermilab proceedings on this. The assumption is that you can get to a number like 10 to the 12th electrons in the beam to produce one muon. But it starts out at a much lower number. So now you ask, you have 10 to the 10th electrons per RF bucket, and you lose somewhere in the phase space tails somewhere between 10 and 1% of the beam. And the attenuation then of the shielding and collimation gets you, in fact, then to this 10 to the 12th number, which is off the graph, off the top of the transparency machine. And so you end up with something like one beamline muon per train. And let's review that just a little bit on this transparency. So the muon rates from conventional sources that we've mentioned are of the order of 100,000 events for 100 inverse picobarns, a few thousand events for Higgs, which involves muons. Beamline muons, if we assume 1 mu for each 10 to the 12th electrons, then if we look at the RF structure, the NLC and at least one version of the JLC, which is the same, has 190 pulses with a rep rate of 120 hertz in the case of NLC. So that means your detectors would be sensitive to one single train, which is 266 nanoseconds long, which has 190 buckets. And eventually then that gives you, when you divide by the 10 to the 12th factor, about 1.5 mus per train. You can go through the analysis for the JLC in the same way. And Tesla is a little bit different. In the case of Tesla, you have to tell me what the sensitive time of the detectors is. And I've just taken an example, which is 10 microseconds. So there are 20 pulses in 950 microseconds. So in 10 microseconds, there's a small fraction of this, 29 pulses. And at 210 to the 10th electrons per pulse, that gives you about a half or a little more muons per pulse. So that would not seem to be a problem. In talking with Tom Markevich after his talk today, I think we need to look more carefully at those muons that come directly from the interaction region itself, and we'll try to do that. So now let's talk a bit about the muon system specification. How am I doing for time here?
15 minutes left.
Okay. This is a picture of the Tesla detector. The thickness of the iron, which is part of the muon, which forms the basis of the muon system, is determined by the flux return cross-sectional area and how much iron you think you need for for muon identification. In the case of the flux return, it comes to about 1.6 meters in thickness. So you instrument that flux return with some kind of detectors. So you want penetration through something like a dozen interaction lengths of the muon. The precise momentum of the muon is determined and charged from central tracking. You use the hits in your muon detector to link up tracks with the central tracking, and there you would like something like 15 hits to make sure that you don't have ghosts and so on. So you want high tracking efficiency, and then the other thing that one needs is to use the muon system for a tail catcher for calorimeter energy. This is a little bit, I suppose, controversial because we don't understand, or I don't understand exactly the energy flow algorithm. So the candidate technologies are resistive plate chambers and similarly based detectors. And that's the resistive plate chamber case is part of the Tesla design report. And Marcello Piccolo and colleagues have worked this out, studied this in some detail. This is the maximum hit density, the number of hits per square centimeter along the x-axis, the number up here. So in general, the hit density is rather low. Occasionally you get more than 10 hits per square centimeter. This is the case where hadrons leak into the muon system. The efficiency is good. I don't think I'm going to show you that. If you use a number of hits algorithm to indicate the hadronic energy, you can determine the resolution of the calorimeter. The resolution of the muon system is used when used as calorimeter, and that's given here. It turns out to be 135 over the root of E with a 20% roughly constant term. That's right, isn't it? Yes. Now, so the scintillator-based system, why would you want that? You might think that you need additional calorimetry because the calorimeters are in fact not all that thick. Now, Ray has just talked about this a little bit, and I'm not going to contradict him, but this is, for example, the Tesla calorimeter is about 5.4 lambda thick. The large NLC detector is about 6.7 lambda thick. And so the things that you're probably going to want to know about are the hadrons, in particular the neutral hadrons that escape the regular calorimeter and go into the muon system. This discussion of sampling calorimeter is not exactly applicable to this question, but it's interesting, and it's the thing that should cause us to think hard about this. So this is a result which is, I think it was 1980 roughly. Pat Dishaw, a thesis student at Stanford, worked on an experiment where there was a sampling calorimeter 30 inches square, and it had a total of about 11 interaction lengths. This is a plot of just the sum of the pulse heights in that total of 49 counters. The arrangement is listed here. Now, if you decide that you're going to stop at counter number 30, which is the first 20 of these and the next 10 of these, so that you're at 7.58 lambda, then you get the dash curve, which shows that you bias the mean and you get a low energy tail. And so that's the thing that one wants to focus on to some extent. So how would we instrument this? Well, this is just a cross-sectional a typical cross-section octagon with, in fact, 15 or 16 4-inch steel thick plates, 10 centimeters. Then you can look in the gaps, which we've assumed are 5 centimeters. This is a picture of how one might instrument that. Just to show that you can stuff stuff in there. This is with some detectors made from probably the only piece of hardware you'll see at this meeting, which is this thing right here. It's a piece of extruded scintillator. You can pass it around and look at it, distract you. But that's 1 centimeter thick stuff. So we assume a module is going to be about 1.5 centimeters thick. In a 5 centimeter gap, you can stuff that in there, and you can overlap them because you may not want to make detectors that are 5 meters across and 9 meters long. The general scheme would be to have these 4.1 centimeter strips forming a UV plane. So this is the length of the thing, which only goes to 4 meters here, but it's actually 9 meters long, and it's the half width of the largest gap is 2.5 meters roughly. These strips then are a maximum of 3.75 centimeters meters long. Sorry, there are about 200 of these strips per module. If you have 16 gaps, then this number of fiber ends, 90,000, is really 102,000. And you're interested in knowing what that does for you. Let's see, somewhere. We have to get back to the original page. So this is the proposed layout down here, and you've seen a little bit of it. You take these modules that are 9.4 meters long, and they vary in width from 174 to 252 centimeters, and they're 1.5 centimeters thick. You make, in the 16 gaps, 8 U planes and 8 V planes. Now, you get then light out of the scintillator strips from both ends, and if you look at the number of photoelectrons, this is the plot from Minos. Minos uses exactly this stuff which is going around. That's why it exists. Then the maximum length of the strips in this case was 3.6 meters. So at the far end, you get 6 photoelectrons, and at the near end, you get 11. So you get between 6 and 11 photoelectrons. So on average, you've got a fair number, and it looks entirely doable. So I want to spend now just a couple of minutes on R&D issues. Physics analysis for detector designs. We really need to understand the shower leakage into the Muon system. We need, to do that, we have to have tracking detector studies. We need to incorporate any energy that's found in the Muon system into the energy flow analysis. We have to understand how that helps. Is it worth the price? We need to make sure that we understand the Muon system response to a broad spectrum of physics processes. And in fact, at 1 TeV, because I don't think too many studies have been done at 1 TeV. There are a lot of questions about module layout, cell sizes, materials, readout techniques, which leads us into the question of electronics, evaluation of existing designs, what size, how many fibers per scintillator, what the fiber arrangement is, the routing of cables, the diameters and so on, the front-end electronics, what the multiplexing and readout schemes are, and then there's a whole issue, of course, of software and firmware. The mechanical engineering is interesting. And then we come eventually, after we've digested all that, to some prototypes. We need to write an R&D proposal for this prototyping stuff, which includes things like manpower and budget and testing needs. Eventually, I would guess that these detectors will have to be tested in the test beam, and this isn't just the Muon system, this is all detectors. So there will probably have to be some kind of a proposal for a test beam, and finally there's the experiment itself, which we all need to get to. That's the object of the game. Okay, that concludes my remarks on the Muon system possibilities. I want to talk a little bit about the session tomorrow at 2 p.m. in room 208. It includes particle ID. Our particle ID expert feels like he's the Lone Ranger because he gets stuck with the Muon guys all the time. So that's Robert Wilson, who's sitting right here. Raise your hand, Bob. He heard Grannis say this morning that one of the things that probably is important is the determination of flavor. That could be interpreted as particle ID, I think. So that's something that Bob will help you think about if you give him half a chance. And then we have an update from Piccolo on the Tesla design, some issues of aging studies for CMS, NCAP calorimeter chambers, update on Muon, Mino scintillator, the stuff that's passing around, and some preliminary studies on hadronic shower leakage and costing methodology. I think I'm going to stop there.
So thanks for that talk. Do we have any questions for Gene?
They're all asleep, huh?
Okay, break for the talk. Oh.
Ah, Ron. What's up?
I mean, you mentioned two possible technologies, but there would also be...
there could be others, yes.
Yes, like streamer chambers.
30 different technologies,
yes,
right.
So why did you select only... no, but...
That's the only two that we've heard from. I mean, well, that's not quite fair. We have had discussions at previous meetings about regular drift chambers, for example. There's not very much written. We really need to, if we're going to put our cards on the table, we have to say what they are. I mean, this doesn't count to just think about things. You've got to write it down. So I think that's one of the issues. Anybody else?
Time for one more question. Okay. Well, thanks again to Gene for talk.